So now that we are done with this, we can go ahead and start working on our actual list, which would be a doubly linked list. So doubly linked list. So basically it takes the same things. So this one is an any type. This one here would take a previous field, which is a meta field enum of t, and of course the same next filed for some reason. Just want to file things. Field. I can't do this. I can't do this. Right. So here we are going to need a self, which would be at this, and we are going to need a prev, which would be stud meta, I think, field info, yes, t, and prev field and name. Yes, and here we're just gonna do prev comes next. Cool. So let's take a look at what functionalities or what functions the Zig implementation provides, and we are just going to do the same. Actually, I could have copied the description as documentation, but you know. Right, so here I'm just gonna remove these things. There we go. Right, so and then we are just going to do a quick this, and we are just going to do something like this. Yeah, that should be fine. And then if we do this, right, and we can do cool. Very nice. So now I think we can just so what's it complaining about here? Expected statement but found pub. Okay. No, it's not it. Am I missing something here? Oh, right. Okay. Yeah, I'm missing something. Cool. Right. So we should also just do this and change node to t. I guess all of node to t, and we should probably reorder these. So I guess I want pop first, and then pop, and then I want insert before and after, and I don't want to concat by moving. I want to so I guess concat by moving would be stealing items from list 2 to put them into list 1. Or rather, yeah, so it's going to link list 2 to list 1 and then set list 1 to basically not have any items. I'm not sure how it's doing that. So let me just take a look at what they mean by concat by moving. Right, so they set this to null, this to null. So basically they just, it's basically a C++ move constructor. Right, okay. Okay, but then can we actually get a, I don't feel like we need this. Let's just call this concat. We are just going to concatenate list 1 to list 2. And this one we are going to take as const since we are not going to modify it. Right, cool. So we have all our things here. We just need to set up head, which would be a nullable, an optional pointer to t, defaults to null. And we are also going to need a tail, which is also a optional pointer to t, defaults to null. Right, so prepend is pretty much the same as we did before. So can we just go ahead and copy this? Right, actually, I'm not going to copy it. I'm going to re-implement it. So if we have a head, that means that we also have a tail, and that also means that if we do our work on the head, the tail should be untouched. But if we don't have a head, so in this, so here we should have a return, and here we are going to do field head dot, or rather, prev is equal to new node, right? And we are going to do self dot head is new node. Right, and we return here. Yeah, let me just do this. I want to have list is self. Yeah, cool. And I'll just go here actually and do this and do other. Right, so if we have a head, we basically take the previous of that head, set it to our new node, set our actual new head to our new node, and we should be done. Otherwise, we should set head to new node and tail to new node, because and self.tail to new node. And we should, yeah, that looks pretty good. So let's think about this. The weird case happens if we have no nothing here. So we are in the case where we have nulls. Both of these are null. So in that case, we should set the head first. This looks okay. Otherwise, we set the head and the tail, since we don't have them. That looks okay. Right, so append here should be fairly similar, but we are using the tail instead of the head. So if we have a tail, we take the next field of our tail, we set it to new node, and we set our self.tail to be new node. And of course, we return from there. Otherwise, if we don't have a tail, that also should mean that we don't have a head, and that means that we should set head is new node and self.tail to new node. There we go. So it's pretty much the same implementation we did before. It's just the bookkeeping that's a bit different. So we want to pop the first item. So if we have if self.head as h, so if we have a head, we basically set we need to const popped item is what I called that before. This one should be self.head. Yes. So here we have self.head. So we do have a self.head. So we can do self.head is equal to field of so age and next. Yes. And we should not forget to set self.head, or rather at field of our new self.head, or the previous field of that, to null. But here we have a problem because we probably don't have self.head. So self.head as new head, something like this, something like this. This one here should be nh. NH I said. There we go. So we have our, if we have a head, we take the next field to that. If that new field, if that next field is also set, we set its previous field to null. And we, at some point here, we should return popped item. Yes. Nice. So pop here should be pretty much the same. So popped item item is self.tail. Yes. If we have a tail, and we capture that as old tail, might actually be old head. Let's do it like this, okay? So old head, and here let's do new head. New head. Yes. So old tail. We do have this, so we are going to go ahead and do self.tail is so field old tail previous, obviously, since we are moving backwards. And if our self.tail, so this new tail here, new tail exists, it's not null, we should go ahead and set its new tail next field to be null, since we removed the next item, which is this item here. So here the question that remains is, do we fully detach this popped item from our list by setting its new and so next and previous fields to null, or do we just leave it and return it as is? That's the main question I'm asking here. And you know what? I think we are going to do that. So if self, or rather if popped item as, we capture that as, what's a good name for this? Let's just do pi. So popped item, or rather add field of pi next is null. And here we return it. And this one is our singly linked list. And here we are going to go to our doubly linked list and do pretty much the same. So if popped item, get that as pi, we do field pi priv is equal to null, and there we go. So this one is next is equal to none, to null, and here we should do pretty much the same thing here, and we should return popped item. Yes. Just thinking here for a bit, we might have missed something, and I think we did miss something. So if we have no head, so what happens if we only have one item on our list? So here we have that one item, here we have this, that one item's next field would be null, so this new head would be null. We are not going to go into this, and our head would be null. but our tail would still be that field. Yeah. So we do have an issue here. So we have a new head. So if we do have a new head, we should set that head's value basically to be null, or previous value to be null. But if we do not have a head, we should set self.tail to be null, because that means that we don't want this tail here to be pointing to some node that we just popped off. All right, let's keep going. So here we should probably have the same thing. We'll come back to this when we write our tests. That's what they are for. Right, so here we want to insert before. So we have a node t, and we want to insert new node before node t. So it's pretty much like a prepend, but we have a node t instead of our head. So yeah. So if, and here we are assuming that node t is not null, so it should exist. So if we, I guess there are no checks to be done here. We just need to set, no, there are checks to be done. So const, or rather var, node priv is at field of node and priv. Right. So this one is, so for example, node 1 goes to 2, goes to 3, and, or rather, let's do 3 and 4, for example. And we want to insert node 2. And we know that these are doubly linked lists. So what we want to actually do is first get node 1, create a link between that node 1 and node 2. And then we want to take node 3 and create a link in between 2 and 3. So we drop the link between 1 and 3 in 2 steps. So this one here, node priv, is our node 1. So let's do what we just said. So node priv, we should probably set its field, but only if it exists. So if we have node priv as np, no problem. So field of np next should be set to new node. Yes, if it doesn't exist, if we don't hit this if here, that means that node is our head. Yeah, so we should just keep going. So now that we've created a new link between node priv and new node, we should create a backlink between so new node, or rather at field of new node, and priv is np. Actually, it should be node priv, and we should always do this in any case. Yes. Looks good. So again, if and then we do field node next, new node next is equal to node, and field of node priv is equal to new node. Because these are the two nodes that we know exist. We have them here. We know that node and new node exists. So variable is never mutated. What do you mean? Of course it is. Maybe I should do something like this, and this should be a nullable pointer of t. Okay. Right. Well, let's say to const and see what's going to say next. Right. So I'm just thinking about what cases we might have missed in our insert before. The only case we might have missed is if we have an empty list, but in that case, we should not have a node. So if we have a node T, we should know that our list is not at all empty. Yeah. Right. So I guess we didn't need that. Maybe we could so debug assert that self dot head is not null. Yeah, and self dot tail is not null. Maybe we could do something like this. Right. So here, insert after. I guess we are going to do the same assertion here. This one we are going to need the next node. So node next is at field of node next. It's fairly symmetrical to the logic we did before. So if we have a next node that we can capture as an x, yeah, sure, it's better than an n. So what do we do here? We get that nx node and we get the previous pointer to our node, and we set that to new node. Yes. And in any case, we are going to set new node next pointer to, hold on, let me think. We are inserting this after, so next pointer would be node next. And in any case, we should basically set our new node priv to be node, and we should set our node next to be new node. Yes, there we go. Cool. So here we want to concat these two. So basically need to do self.tail is equal to other.head, and other.head is equal to self.tail. Yeah, okay. So const all tail. So this one would be self.tail, and this one would be all tail. Yes. No. What? This is wrong. So we want the next of our tail to be their head. Yeah. So we want a field of our. So basically, if we have a tail, there we go. If we have a tail t, we should do this here. We should have t. The next pointer of t should be set to other dot head. Yes. And we should also set the other dot head. Right. So if we have so let me think, what's the best way to do this? So basically we need to do a four-way connection. We need to So let's write the plan. Step 1, connect. So forward connect. I'll call this forward connect tail to other head. Then we backward connect other head to our tail, right? So that means that now we have one continuous list, and then we set our tail to other.tail. Yes. That's pretty good, I think. So are there any weird cases or edge cases? So if we don't have a tail, if we are an empty list, we connect our tail to their head, but then we need to manage our head. Head if empty. Yes. What if they are an empty list? We connect our tail to their head, which should be null, which means that we change nothing. And we connect their head to our tail, which is null, so that changes nothing. So we just need to manage if we are an empty list, if self is empty. And we set tail to other.tail. Yeah, so that we do that in any case. So here we just need to manage if self.head, hold on. So else, if we don't have a tail to connect, that means that we basically become the other list. So else self.tail is equal to other.tail, and self.head is equal to other.head. Yeah, we become the other list. It's my list now. Right, so what's the next thing we need to do? So if we have other.head, yes, capture that as OH, then we set our field of OH, so the previous field of that, to basically ourselves, so self.tail. Yes, and in any case we set self.tail to be other.tail. That means that this can be removed from there. Okay, I might be missing something, but at least it makes sense. Right, so here we need to basically remove a node from a list of nodes. I'm just going to go ahead and copy what we did somewhere over here. Yes. So we just need to rethink the bookkeeping for our previous nodes, but overall it should be okay. So we have a head. That head is our node. If it's our node, then we just set our so we set the next field of our head to head, and we should set the previous field. So if self.head as new head, we should set we should set field of new head, and the field is priv to null, because we are the head. We don't have a previous state unless we want to have a ring buffer linked list where the head would point to the tail for some reason, but we don't want that here. Right, so this one looks okay. We can look at this one here. So we have a cursor, which is our head at any point. We get the next. If we find it, then we set the cursor's next to be our nodes next, but it also means that we should set our nodes previous. No, hold on. We should set our nodes next value here, or its previous to cursor. Yeah. So here we need node next. So this one is at field node next. And here we can do something like this. Yes. But here we want to set our node next previous field, but only if it exists. So if node next, and we'll capture that as an X. So field. We want to set that node's next previous field to be cursor, I think. Of course, here is an X. Right. So, and I guess we should do pretty much the same thing. Yeah, it looks pretty good, I think. Right. Okay. So now I'm starting to think, do we need to split these things off to their own files? Actually, I'm going to try something first. So tests list .sig. And I'm just going to go ahead and do this, go over here, do that. We should probably just const stud is, there we go, and const single linked list is import list.zig single linked list. Same goes for, should we do something like this? Okay, and this one here needs to be doubly linked list. There we go. And this would be doubly linked list. Yes. Right, so now we have our tests, our list tests in here. So can we actually do something like, so test, and can I do import tests list.zig? Is that something we can get behind? Okay. Okay. Const test is that. So how do we go about this? Maybe something like this. What's it complaining about? Oh, so it's just complaining about the actual value. So maybe this can actually give us some edge. Oh, pretty cool, pretty cool. I'm very chuffed with that. Right, so now we can actually do right, hold on, let me do this. Let me get rid of the main, since we're not gonna need that. Do we keep on putting these here, or should we probably do, so list, and we want singly linked .zig. Right. Maybe we should do this and rename this to singly linked. Yes. Yes, that's very good. So now if I go all the way here, can I do singly linked list? And can I actually also do doubly linked? Yes, doubly linked. Cool. So let me just try enable to load. Yes, okay. So this one here. Oops. Let's not upset this guy. Right, so this one here should be something like this. It's not really the best way to go about this. I think I should have created a module, but yeah, it's fine. So in doubly linked, okay, cool. It's pretty cool. And here we can get rid of this. We can actually get rid of pretty much all tests. And here we can get rid of this. And it should be fairly happy. Of course not. Yes, we forgot to do this. Cool. Cool. Right, so now we can actually get to work on this without having to look at all the tests all the time. Cool. So let's do this first. Actually, let's do all of this. And here we can replace this with doubly linked list, and we should have a prev and a next value. So we'll just copy this, set that to prev, and that should be pretty okay. Is it though? Yes, it should be. Here we should do tail, should be null. Length should be 0. Did we actually implement length for this? We did not. We are not going to do that. Right, so I guess we could do const. Okay, that is fine. Very well. So let's do this, go up here, do a bit of this, do doubly linked list, and do prev next. Right. So what do we have here? We have a prepend should increase the length of the list, and of course here we need to so I guess now that we have our own file for this, we could just pretty much get this out of here. And that should be pretty okay. So let's see what we have. So struct is declared here, no field or member function named length. Of course, thank you for pointing that out. And we should have an exception there. Cool, but it's built in, so that's something, I guess. Right, so we have node 1, node 2. We expect this to be equal to that. We expect list.tail to be equal to node 1, and we expect node 1's so head.next should be node 1, and we also expect head.prev to be null. We also expect, so this one would be node 2, tail.prev to be that, and tail.next to be null. Yes. So now let's run this. Let's see where we are. So in prepend should increase test, we expected to have a linked list, but we found null. Which line is that? 29. Okay, so the very first one then. So that means that these two are correct, but this one here is not. So did we not link correctly the right? We did not link our new node's next field. So field new node. Yep. New node. Next is Should we do that here? Maybe. If we have a head, no, we should do it inside here, I think. So new node next is H. There we go. That should solve that. Yes. Cool. Right, so now that we have this checked, let's get to the other ones. Actually, hold on, before we go to the next one, we should probably do the exact same test with append. And we just need to change prepend to append. And if we run that, of course, can we actually just have something? Right, so I think we should have the same issue on append. So if we go to here, right, did we forget to do that again? Yes, we did. So new node, first of all, new node, dot priv is equal to t. Yes. No? So what is the error here? Line 42. 42. So still the same one. Of course. All of these should be inverted because we are appending instead of prepending. There we go. When we do things correctly, we do actually get the results that we expect. Who would have thought? Let me just change this to append, and then we prepend. It should not change much, but I'd still want to also check the interaction between append and prepend somewhere. So pop first should decrease the length. Actually, we should rename should correctly set next and priv. Yes. So this one here, we have no notion of length anymore. So pop first should return the first element. And set, yeah, I don't want this to become a book. So what do we do here? We pop first, we pop the first element we expect it to be node 2. Then we pop the second element we expect that to be node 1. And I'll just add a bit more testing here. So we expect null in list.head, yes, and we expect null in list.tail. We also expect equal. So null. So popped node 2 or node 1, sorry, dot field popped node 1 priv. So we want this to be detached, so we also expect no next, and I should probably do the same thing over here. So change that to 2, and we should be good to go. Right, so let's okay, field, of course, pop node is so it needs here, needs that, needs this. And I guess we have the same problem here. Yes, cool. So up till here, we are doing fairly okay with our implementation. So did we have a pop? Yes. The last element. And here I'm just going to do both of these as appends, so that we know that the last element, or rather the first element to be popped, should still be node 2. Of course, if we don't call the function we want to test, we are not going to get the result we expect. Right, so here we have pretty much the same things to uphold. And of course, we have an issue. So 92. Okay, so head is not set correctly for some reason. Let's take a look at pop. Right, so if we have a tail, so I think, without looking at the rest, I think we just made a typo here. So if we have a new tail, otherwise we should set head to null. Let's see if that works. And it does. Cool. Right, so removing, actually, hold on. Do we have something else to test? Insert before and insert after. Right, so let's, so insert before should insert a node before the I think I'll get it. I'll get it with just this. I'm just going to take these, and I'm going to create a node 3 with value 456, probably even a node 4 with value 654, and I'm going to do list.append before. So wait, hold on. This takes my node, so node 2, and I want node 3 to be before node 2. And then I'm gonna do some testing, and then I'm gonna go back and do append before. And I'm gonna say node 2 again, and I'm gonna append actually node 1 and append node 4 in there. Right. So after we do this, we so what expectations do we have here? So we expect equal. We expect so node so node 2, or rather the pointer to that, should be equal to field node 3. So we are inserting 3 before 2, so that should be next. And same goes the other way. So this one here should be 3. This one here should be 2. And this one here should be priv. Yes. Yes. So same goes here. So this one here should be node 1. This one here should be node 4. And we are inserting 4 before 1, so that should be okay. And this one here should be 1, and this one here should be 4. So in addition to that, testing expect equal, and here we are expecting node 4 to be our list.head. Yes, and we are expecting our node no, that's pretty much all we have to pull. So let me just do this and check that we have, oops, we have something that's not wrong. Up and before, there's no field or member up and before. Oh, right. Insert before, right. Right, okay, of course. Insert before bfire again. Just fire. Right, so 114, and we are not updating the head correctly again. So insert before. Right. So somewhere here, we should handle the case where node here can be the head. So if node.previous, if we don't have node.previous, that means that we are the head. And we should set self.head to, Yes. Very, very nice. This is going swimmingly. Right. Do this again. Put that in there. And then here we want insert after is what we called that. So insert after, yes. Insert after. Okay, so let's reread this. We want to insert 3 after 2. Okay, and we want to insert 4 after 2, actually. And we want to make sure that our tail is 4. So we insert 3 after 2, so 3's previous should be 2 and 2's next should be 3. And same goes here. No, hold on. We changed this. So we expect node 4's previous to be node 2. So this one is prev and this one is next. So we expect node 2's next is to be node 4. And we might be wrong about some things. So 1, 3, 5. I guess it's the classic. We forget about updating the head. So self.tail is new node. Sorry. There we go. And we still have an issue here. So what's going on? We expect node 4 to be the tail. What did we do in our test? We insert node 4 behind node 2. Well, actually it should be behind node 3. Right. Oops. One too far. Okay, so if we do the tests correctly, we should be fine. Right, so I guess we have concat, and then we have remove. So let's put this back. So test concat. This one would be fun. So we'll need to create 2 lists. So list 1 and list 2. And here we have list 1, we append 1 and 2, and list 2, we append node 3, and list 2 dot append node 4. Yes, okay. So here we want, so list 1 dot concat. Yeah, that's it. List 2. Yes. And now what we need to do is we need to try set this thing expect equal. So we want list 1, or rather node, the pointer to node 1 to be equal to list 1 dot head. Let's start with the basics. Then list 1 dot tail should be equal to node 4. Yes, we are appending, so it should be node 4. Then we should also expect equal. So what are we expecting here? We want to do checks on list dot or on node 2. So at field node 2 next. Yes. So we want this to become node 3. Yes. And finally, we want node 3's previous, not 3's previous to become node 2. Yeah. Looks okay. Oh, that actually worked first time. I was expecting a bit more of a fight from this. Okay, so I guess we should also test the edge cases. We do have a few edge cases. Concat with empty list. So we create list 1, we create list 2, we get rid of node 1 and 2, and we should find ourselves doing hold on. So node 4. No. Node 3's previous should be still null. Yes. And we should have in node 4.next, we should also have null. We are not testing the relationships between node 3 and 4 because we know that our append works. We have a test for that. Right. So let's run this and see if we messed up, and we did not. Huh. Hold on, I'm just going to add something here. Set this thing expect equal, and I want list 1, or rather null, list 1 dot head, head, and same for hold on, same for tail. Okay, so this one is holding. Cool. This is going way better than I expected. Right, so we have our list, we prepend that, we remove that one element, and now we should actually check that our tail is also set. And I guess we forgot the tail, to set the tail. So remove. If we have a head, if we don't have a head, we are basically empty. So we should set self.tail to be null. Yes. Yes, sir. That looks okay. Right, so now let's bring up the second test for this. And we expect this to be, so we don't have results in empty list. That should be fine. Removing node, that's okay enough, I guess. So here we prepend 1, 2. Sure. We remove 2, which is the head. Then we try to remove 2 again. Right, so hold on. Let's see here. We have 1, 2. We remove 2. 1 should become the tail and the head. We try to remove 2 again. This shouldn't change. Yes. We append with 3, and we remove. And we remove node 1. So that means that here we have 3 should become the head, the tail, and everything in between. Actually, hold on here. When we remove a node, it just goes to its owner. Right. So we are not allocating any memory here. We are just getting pointers. So we are assuming that every single pointer has an owner that manages its lifetime. Right. So here, is there a case I'm missing? Is this an obvious case I'm missing? Am I ever removing stuff from the middle of a list? I don't think I am. So let's add another value here. Put this as 654, the classic. And here I want to, so here we have 1. We add 3. And I will also list prepend with node 4. So here we have 4, 1, 3 are our lists. So head should be node 4, and tail should be node 3. And here we can do check on so expect equal. So node 3 should be field node 4. So next, yes, next. And we should also do pretty much the same thing here. So replace that, and that should be cool. And if we do brief here, we should be fine. Yes. Okay. I'm pretty shocked that this went so nicely. Okay, so now we do have a pretty usable linked list implementation. Are there any features I can think of right now that I'm going to need for this list? By the way, if you haven't seen the last video where I explain the grand plan for the allocations on FLCNOS, then go watch that and you'll understand why we need linked lists. Enough yapping for now. Let's wrap this up. Well, that's pretty much it for this one. Linked lists implemented and tested. As always, if you've enjoyed this content, leave a like, subscribe, and if you have questions or remarks, leave them down below or join the Discord. Until the next time, I'll see ya. Fucking out.